Hello, folks. We will continue our homework spree with Chapter 11. We'll work through problems 2, 3, 4, 13, and 18. A little bit more labor intensive than last chapter. So, we'll go ahead and get started. Chem. Okay, the first problem, Chapter 2. Chapter 2 has us looking at the solubility of oxygen in water is at 25 degrees is approximately 8.5 milligrams per liter. At essentially the standard pure pressure, in the same temperature, what is the volume of gas occupied by 8.5 milligrams of oxygen? So, we're turning 8.5 milligrams in a liter into what volume would 8.5 milligrams of gas be at standard pressure. So we're turning that 8.5 milligrams into a volume. So the first thing we start at 8.5 milligrams, we're going to turn that into a mole. So there is 1,000 milligrams in 1 gram. And there is 32 grams in 1 mole. This should give us something like 5 divided by 1,000 divided by 32. 2.65, let's say 6 times 10 to the negative 4th moles. 25 degrees, that is 298 Kelvin. And standard pressure, we'll just, if we say 1 atm, standard pressure, that means our R is 0.08206. So volume equals 2.656 times 10 to the negative 4th times 0.08206 times 298. Now, all that's assuming you have one atmospheric pressure of pure oxygen. That's assuming you have 1 atmospheric pressure of pure oxygen. However, the standard pressure of pure oxygen is not 6.50 times 10 to the negative 3rd. That's assuming that's 1 atmosphere of pure oxygen. But oxygen is actually 0.2095%, 20%, essentially, almost 21% of 1 atmosphere. O2 in 1 atmosphere of air. So they want us to instead divide our number by 0.2095 instead of 1, and you get instead 3.1 times 10 to the negative 2nd liters. Converting that into milliliters, you get that would be approximately 31, so times back by 1,000, 31 milliliters. So instead of filling up 1 liter, that same amount of gas should fill up 31 milliliters of our atmosphere. Problem 3. Now, at 30 degrees Celsius, the solubility of oxygen is 7.5 milligrams per liter. Consider a water body at that temperature contains actually 7 milligrams per liter of oxygen. And by photosynthesis, 1.5 milligrams of carbon as carbon dioxide is converted into organic biomass using it during a single hot day. Is the amount of oxygen produced at the same time sufficient to exceed the aqueous solubility? So we're going to use 1.5 milligrams of carbon and this reaction, we're going to use that CO2 plus water goes to a generic CH2O and O2. So that's the generic reaction we're going to use. So, and then the final thing is, okay. So how much would 1.5 milligrams of carbon produce? So carbon is 12 grams per mole, so that'd be essentially 12 milligrams per millimole. Milligrams per millimole, that's fine. And that would produce, and for every 1 millimole of CO2, we would produce 1 millimole of O2. And oxygen has, for 1 millimole, would produce 32 milligrams. With that in mind, 1.5 divided by 12 times 32 means we would produce something like 4 milligrams of oxygen. 4 milligrams of oxygen, with that in mind. Now, if there's already 7 milligrams per liter, that could potentially oversaturate it. So how much water would need to be present for this to not saturate it is the question they should have asked. And so if we can afford to fit in 0.5 milligrams per liter, 0.5 milligrams per liter, you would need what, like, if you times this by 8 liters, you would get your 4 milligrams. So if you had less than 8 liters of water, this would exceed the solubility. This would exceed the solubility. But if you had greater than 8 liters of water, it would not exceed the solubility and you would be fine. So, question 4 is just more of a thinking problem. More of a thinking problem where we have to reason this out. Thermal power plants, whether powered by fossil fuels or nuclear energy, discharge large quantities of cooling water into a lake or river. Discuss the meaning of thermal pollution in the context of this chapter. So basically, if we dump a bunch of hot water into a lake, what's going to happen? The water temp is going to go up. As it goes up, the solubility of gases goes way down. So in this case, oxygen content would go down because the hot water would mean less oxygen could dissolve. So in these cases, fish and other organisms would be harmed. They would have less available oxygen. to use, and so that would cause stress to them. So, but that's all we're looking for. That's all really we're looking for. Kind of a thought process of, well, if that temperature has an opposite effect on solubility. That as temperature goes up, solubility goes down, and so a lot of other species are going to have trouble breathing because of that. So jumping straight to problem 13. Straight to problem 13 after that. So 13, calculate the alkalinity of water that is in equilibrium with the atmospheric carbon dioxide and contains and the additional species except those resulting from that and no additional species except those resulting from this equilibrium. So we're basically looking at this situation. We're looking at this situation. So we're looking at the CO2 plus water goes to H2, well, actually, CO2 gas goes to CO2 aqueous. Then we're going CO2 aqueous plus water goes to H2CO3 aqueous, and H2CO3 aqueous plus water goes to H3O plus aqueous and hydrogen carbonate aqueous. Then finally hydrogen carbonate aqueous plus water goes to H3O plus hydronium and carbonate aqueous. Now, essentially, there's a lot of fancy equations, but as long as we know a lot of constants, we can find these things largely in terms of just pressure of CO2. So if we can find the pressure of CO2, we can find everything else. So now, depending on the book, you may or may not consider this part, but so the pressure of CO2 is going to be, I say, the pure pressure minus P of water times the normal proportion of CO2, which is 387 times 10 to the negative 6 at 25 degrees. Since the book made such a big deal of including the vapor pressure, I will. So the normal pressure is 101,325, and then the pressure of water is 3,200. And so that subtraction gives you 98125. And when we multiply that by the 3.8, 10 to the negative 6th, 981. Okay. I'm guessing there's no decimal. There's no decimal there. It's 387 times 10 to the negative 6th in terms of pascals. And so this gives us the pascals of CO2 is 37.9 pascals. Now, some various useful constants here. And these are all stuff you can look up, and this is what I did. K sub h is 3.3 times 10 to the negative 7th. Ka1 is 4.5 times 10 to the negative 7th. Ka2 is 4.7 times 10 to the negative 11th. So starting off, we want to find the concentration of CO2. The concentration of CO2 in water is equal to Kh times the pressure of CO2. So it becomes 3.3 times 10 to the negative 7th. That's molar per Pascal in this case, times 37.9 pascals. Our concentration of CO2 becomes 0.3 times 39, and we get something like 1.25 times 10 to the negative 5th molar. Now, based on the equilibrium expression, we're going to bypass the carbonic acid, and just relate the CO2 to the acid and the CO2 to the. So this is our pressure. This is our CO2. So we're going to bypass the carbonic acid and just relate the CO2. We're just saying the CO2 plus water. 2 waters goes to reversibly to hydronium and hydrogen carbonate. We can say that the Ka1 is equal to x squared over our CO2 aqueous. Since we know Ka1 and we know our CO2 aqueous, we can find our x. So we're going to say x equals 4.5 times 10 to the negative 7th times 1.25 times 10 to the negative 5th, square root that whole thing. You square root that whole thing, you get x is 2.37 times 10 to the negative 6th, and this is equal to hydronium and hydrogen carbonate. Now with that in mind, we can find carbonate concentration through this handy equation that relates this to the CO2 concentration times Ka1 times Ka2 all over hydronium concentration squared. So find everything in terms of just that, and so we have, okay. And so solve that, we can have that, okay. Carbonate is 2.3, let's like 4.5 times 10 to the negative 7th times 4.7 times 10 to the negative 11th times, we said, our 1.25 times 10 to the negative 5th, all divided by our concentration of acid, which was 2.37 times 10 to the negative 6th squared. And so, all in all, you get 4.71 times 10 to the negative 11th. So essentially, looking at this another way, Ka2 equals carbonate times acid over carbonate. And since these two values are the same, these cancel out and you're just left with shit. Now, if we want to calculate proper alkalinity, we can turn OH minus concentrate, H2O plus concentration into OH minus concentration. And so Kw is 10 to the negative 14th divided by our 2.37 times 10 to the negative 6th. And that gives us, what? 4.27 times 10 to the negative 9th. So if I'm trying to calculate all of my alkalinity here, we're going to have effect of, from carbonate, it's 2.37 times 10 to the negative 6th. We're going to have our OH of 4.27 times 10 to the negative 9th. And we're going to have our double effect, two carbonates, 2 times 4.7 times 10 to the negative 11th. But we have to subtract out our acidity, which is subtracting out our 2.37 times 10 to the negative 6th. Dang it, sorry. And so that part cancels out, that part cancels out. So largely it's this. But 4.27 times 10 root negative 9 plus 2 times 4.7 times 10 to the negative 11th changes this up by just a smidgen to 2.36 times 10 to the negative 9th alkalinity. It's largely just the alkalinity. Yeah, it's largely just the OH minus concentration, but the carbonate does provide a little bit of a tweak. So that was a massive problem, but some of it made it a little bit harder than it had to be. So with that in mind, 18 is a similar problem. 18, as says, the surface water of open area of the Indian Ocean adjacent to Kenya has an alkalinity of 2,320 micromoles per liter and a total carbonate of 2.03 times 10 to the negative 3rd moles per liter of, so that's HCO3 minus, and the CO3 2 minus. They want us to calculate the HCO3 minus, the CO3 2 minus, and something like the pH. So the basic idea here is we're going to kind of work in reverse. So HCO3 minus plus OH minus plus 2 times our carbonate minus our acidity is going to equal 2,320 micromoles. But we also know that our carbonate T is going to be equal to CO2 plus HCO3 minus plus CO3 2 minus. We're going to use our atmospheric CO2 pressure to calculate CO2 concentration and plug it into our carbonate concentration. If we assume the hydronium and hydroxide are negligible, then we can subtract the two equations to solve for carbonate. You get hydrogen carbonate. So we only need Ka1, hydrogen carbonate, and carbonate to get the hydronium. So let's go ahead and get started. Okay. Our total carbonate is, we said, essentially 2.0 3 times 10 to the negative third. What 2.0, another way to look at it is 2030 micromoles per liter. So really, the hydroxide is providing a little bit, but not too much in terms of this. However, the CO2 is also contributing to our total carbonate, so it could be producing more. So with that in mind, we're going to follow some of the same steps. So okay, so follow some of the same steps. So let's see. Okay, so let's try to solve this. If we make this mention that same thing, we'll just actually neglect. I know they don't give us a temperature, so we're going to neglect the effect of water on we're going to neglect the effect of water on our pressure of CO2. So we say the P of CO2 is going to be equal to the 101,325 times the 387 times 10 to the negative 6. The same way we did, except we're neglecting the vapor pressure. 101,325 7 times 10 to the negative 6. So that'd be 39.2 pascals. So CO2 concentration would be, hypothetically, let's say KH 3.3 times 10 times 39.2 times 10 negative 39.2 2936 times 10 to the negative fifth. That's CO2 concentration. So with that in mind, let's see. That's 12.9, we'll say 12.94 micromoles of CO2. .94. So if I subtract that out from the total, 2030 minus 12.94, that means we have 2017. CO2 is going to be HCO3 minus and CO3 2 minus. Now, if I say 2017 minus H carbonate equals carbonate, actually, I'll do it the other way around. Minus carbonate is equal to H carbonate. What we have, we plug that in, and you have a negative carbonate plus a positive carbonate. You have 2320 equals 1 essentially negative carbonate equals 2017 plus carbonate hydroxide. If we say these guys are relatively small and negligible, we can say that carbonate must be 2320 minus 2017, 303 micromoles per liter being carbonate. And then that means hydrogen carbonate must be the missing amount. So 2017 minus 303 would be 1714 micromoles per liter. And that leads us finally to the idea that hydrogen carbonate over carbonate times hydronium equals our Ka2 of 4.7 times 10 to the negative 11th. It doesn't matter that the units of these because they'll fix themselves. Micromoles and micromoles work themselves out. So 4.7 times 10 to the negative 11th. Okay. Times the 1714 divided by 303 would give us our hydronium concentration. So 4.7. See if this actually looks reasonable in terms of hydronium being negligible. 14 divided 4.7 times 10 root negative 11 times 1714 divided by 303 gives us on like 2.65. We'll say 66 times 10 to the negative 10th. Turning that into micromoles would be, that's very negligible. Micromoles, that would be something like 2.66 times 10 to the negative 4th. So a fraction of a fraction. So negative log of that gives us a pH, 2.66 times 10 negative 10th means we have a pH of something like 9.56 being the pH. So it's pretty basic. I mean, it's pretty basic for seawater, but not too horrible. I mean, it takes a little thought, but we can do it. It's there. We got it. It's a little tricksy. But okay, so that is that last problem. Now, I guess if you would have got slightly different numbers had you included let's say water vapor pressure, but I think that's pretty good. Now let's see, hydroxide might have actually been somewhat significant in that case. Let's see, 2.66 times 10 to the negative 10th. We take 10 to the negative 14, divided by my answer there. I mean, OH minus would have been like 37. So it plays an effect. It tweaks your numbers. It tweaks your numbers ever so slightly. I mean, I think you could probably try it again without ignoring the hydroxide this time and get slightly better numbers. But we're not going to do that. We're not going to do that for right now. Okay, but that's that problem. That one's a little bit harder. Have a good day.